It's recording? Okay. Hold on. Okay. In this video, we're going to talk about the nested interval property. And it's a theorem. So a reference for this is the book by Abbott, Understanding Analysis. It's early in the first chapter. And the theorem says, suppose that we have a bunch of closed intervals. So suppose that for each natural number, we have a closed interval a(n), bn, and let's call this I sub n, okay? And assume that we have I1 contains I2, which contains I3, which contains I4, and so on. So that's what I mean when we say that the intervals are nested. Okay. Then the intersection is non-empty. So it is not the empty set. So in other words, there's some element that's in the intersection. Let's draw a picture to illustrate this. So here's the real number line, and you have I1, which is some interval from A1 to B1. So let's say, A1's here and B1's here, okay? And then you have an I2, which is contained in this interval. So this interval from here to here is I1, and then I2 is a closed interval inside that. So maybe A2 is, I don't know, from here to here, A2 to B2. So maybe this is the interval I2, and then I3 is contained in I2. And it could be that, A3 is equal to A2, and then B3 is here, say. I'm just making this up. And then, so you have I1 contained, it contains I2, and that contains I3. And then there's I4 and I5, right? I4 is contained in I3, I5 is contained in I4, etc. And then you have an infinite collection of these intervals, like I1, I2, I3, I4, and it just goes on forever. And then there must be something in all of them. That's what the theorem is saying. So before we jump to the proof, let's think about what happens if we remove some of the restrictions. Let's think about what happens if we remove the conditions on the intervals. So what are the conditions? We have closed intervals. Okay. Well, first of all, what happens if you don't have closed intervals? So let's say you had open intervals. Now remember, the interval that's not closed isn't necessarily open, but an open interval is not going to be closed as long as it's not empty. So, well, that wouldn't be an interval. Okay, so there's no open interval that's also closed. So let's say that we had open intervals. Is it possible that we have a nested collection of open intervals and then the intersection is empty? Well, if you think about it, let's say that you had what's a good example? A good example would be if you take the interval from 0 to 1 over n. So I1 goes from 0 to 1. Oops. It's the interval from 0 to 1 over n. Okay. Open interval from 0 to 1 over n. So this is I1. I2 goes from 0 to 1 half. I3 goes from 0 to a third. Right? So you have all these intervals, and it's just like 1/4, 1/5, etc., and it just keeps going on forever. So you have I1 contains I2, which contains I3, which contains I4, etc., right? But what's the intersection? I claim that the intersection is empty. Okay, why is this true? Well, suppose because if x, so if x were in the intersection, it would have to be an I1, right? So if x is any number between 0 and 1, now we use a key fact. We use this fact that shows up all the time, that the 1 over n gets arbitrarily close to 0 as n goes off to infinity. So if x is any real number, we can choose, we can let capital N be, let's see, greater than 1 over x, right? Then, okay, now let's make sure we have the signs correct. Then x is greater than 1 over n. So then x would not be in the interval I sub capital N, because little x is greater than 1 over capital N, right? And I sub capital N is everything from 0 to 1 over n, not including 1 over n, or 0. So this gives an example of what happens if we don't assume that the intervals are closed. Because we could have open intervals nested, but with an empty intersection. So the closed condition, well, at the very least, we can say the statement is not true if you just get rid of the word closed, right? If you just take this theorem and then just cross out the word closed, the theorem is no longer true. Okay, so we know that the closed part is relevant. Now that we have an idea of what's going on, what happens if we had, unbounded intervals? So like intervals that just went off to, infinity. Well, if you had something like that, you could have something like, so another example is you could have I1 be the interval from 1 to infinity, I2 be the interval from 2 to infinity, and so on. So just In is the interval from n to infinity. Well, why is the intersection empty? So this is unbounded. The intersection is empty because for any real number x, we let n be greater than x, and then x will not be in I sub capital N, right? Because the INs are moving to the right, right? The left endpoint of these INs are just going by 1 to the right every single time. So eventually, no matter what your x is, eventually the INs will go to the right of the x. Right? So therefore, the intersection is empty. So in order to guarantee a non-empty intersection, there's some condition on the intervals that they're closed and bounded. Okay. Now, no one's saying that if your interval is not closed or bounded, then it's impossible for the intersection to be non-empty. I mean, there are examples where that happens, right? You can just come up with some that are easy, but this theorem provides a sufficient condition to guarantee that the intersection is non-empty. Okay, so now that we have a good idea of that, let's go to the proof. So to come up with the proof, it might be helpful to come up with some examples to understand how we might come up with this proof. But let's just, jump to the proof. Okay. So we have A1 less than or equal to A2, which is less than or equal to A3, which is less than or equal to A4. Right? So these are the left endpoints of the intervals. So I should say we have this. This is a collection of numbers, and what we're going to do is we're going to take the supremum of these, the supremum of the set of these numbers. So let, say, capital A be the collection of the ANs. Okay. Let X be the supremum of A. Well, hold on. Before we can jump to the supremum of A, we have to know that it has a supremum. Now, this set is a non-empty set, right? It's a non-empty set, and we need to know that it's bounded above in order to have a supremum. So before we can jump to the supremum, let's show that A is bounded from above. Now, can you think about what is a number that is guaranteed to be above all of the AIs? Well, B1 is going to be greater than all of the AIs, right? So the set, now why is this true? So for each n, we have this interval an to bn, and we have that they're nested. So we have that an is less than or equal to bn, right? Now, what do we know about bn and b1? How is bn related to b1? Since the intervals are nested, bn must be less than or equal to b1, right? Right, your bi's are to the left of b1. So we have this. So we've shown that for every natural number n, an is less than or equal to b1. So b1 is an upper bound of A. Now that we know, so since A is a non-empty set bounded from above, it has a least upper bound. And let's call this least upper bound X. Now we claim that X must be in the set. By the way, this fact that A1 is less than or equal to A2 or less than or equal to A4, we'll see that we don't actually have to say that in the proof, so we can remove it. What we're doing is we're coming up with the proof. So we claim that this least upper bound is in the intersection. Now that, if you look at some examples, that is what you would think would happen. So basically, you have A1, right? You have A2, A3, and they're just kind of going up. And B1, B2, and B3 is decreasing. So if you think about, what could be in the intersection, right, if A1, A2, A3 is increasing, you would think it would be the least upper bound, the supremum. Okay, so that's why we might suspect that X is in the intersection. So we claim we will show that X is in the intersection of the INs. And once we do that, then we'll be done because we show that the set is not empty. Now let's go back to our proof techniques. How do we show that an element, that a number is contained in the intersection of a bunch of sets, right? We're trying to show that our X is in the intersection of a bunch of sets. So what's the proof technique? What do we have to prove in order to prove that? Remember, we're trying to show that X is in all of the INs. So what you have to do is you have to take an arbitrary IN and show that X is contained in that. So what we have to say is let N be a natural number. We want to show, so we must show, suffices to show, whatever, it's all the same, that X is an element of IN. Well, what does it mean to be an IN? Well, IN was the closed interval from AN to BN. So we want to show that X is greater than or equal to AN and less than or equal to BN. Okay, that's what we have to show. Well, this is a double inequality. We have to show that AN is less than or equal to X. Well, think about what X was defined to be. It was defined to be the supremum of the ANs. So that we know that AN is less than or equal to X since X is, it doesn't have to be the supremum, it's just we know that X is an upper bound of the ANs. So since X is an upper bound of A, right, the set A. What we have to show now is that, going back to our picture, the supremum of these AIs, okay, for any n, it's less than or equal to Bn. So that's what we have to do. Okay, now we have to think about how we defined X, right? X is not just an upper bound of the set A, it's the least upper bound. So we know that X is less than or equal to any upper bound of A. Now we want to show that X is less than or equal to B sub n. So it suffices to show that B sub n is an upper bound of A. Now let's think, could that be true? So could, Bn, for any n, be greater than or equal to all of the AIs? I mean, do you think that's true from the picture? Well, yes. Right. Because, if you look at the picture, okay, you have like A4, B4, A5, B5, and so on. Looks like every B is going to be greater than all of the A's. Right. So how do we prove that? Let's see. Well, first of all, we know that B5 is greater than or equal to A5, right? Now, A5 is going to be greater than A4, A3, A2, or A1, or greater than or equal to, right? And then we can use that argument for for B sub n. So we know, let's see, upper bound of A. B sub n, so now we claim that B sub n is an upper bound of the set A. So now we let, say, A sub k be an A. Now if k is less than or equal to n, then we have A sub k is less than or equal to B sub k, which is, A sub k is less than or equal to A sub n, which is less than or equal to B sub n. Right? So B sub n is greater than or equal to A sub k. If k is greater than n, then, okay, so let's think about how can we show that, say, B5 is greater than A6 or A7? Well, then what we should compare, the kind of intermediate step to compare A7 and B5. How do we know that A7 is less than B5? Because we have a B7 that's in between, right? We know that B7 is greater than or equal to A7, and we know that B7 is less than or equal to B5 because of the nested condition. So now we have our general argument. If little k is greater than n, then A sub k is less than or equal to B sub k, and since the intervals are nested, B sub k is less than or equal to B sub n. So therefore, for all k, right, B sub n is greater than or equal to A sub k. So thus, since A sub k was an arbitrary element of A, we know that B is an upper bound of A. Now, why did we want to show, or B sub n is an upper bound of A. Now, why do we want to show that B sub n is an upper bound of A? Because we're trying to show that x is less than or equal to B sub n, right? And we know that x is the least upper bound. So if B sub n is an upper bound of A, okay, and x is the least upper bound, what does that tell you? That tells you that x is less than or equal to B sub n. So since x is the least upper bound, remember the least upper bound is the upper bound that's less than or equal to any other upper bound. So since x is the least upper bound of A, we have x is less than or equal to B sub n. So what did we do? We showed that x is between A sub n and B sub n for all n. Therefore, x is in I sub n, and since n is arbitrary, right, we just had a generic I sub n, x is contained in the intersection, so the intersection is non-empty. And that completes the proof. So this is, now you might look at this and say, wow, this is very messy. Now, of course, this should be cleaned up, but this has all the correct elements of the proof. Because we took, we proved that our set A has the least upper bound, okay, by showing that it's bounded from above and it's, non-empty. We didn't need to show that. It's, from definition, we know it's non-empty. Then we show that it's bounded from above, therefore it has the least upper bound. And then we did all the steps to show that x is contained in the intersection of the I sub n's. So if you look at the proof in the book, in Abbott's book, he actually skips he kind of glosses over how you know that each B sub n is an upper bound for capital A. He doesn't actually write the proof, at least in the first edition of the book. But I think that's something that should be proven because he doesn't explain why it's true. So this is what a complete proof looks like. Okay, all the steps. So let's try to summarize the proof. Okay, you take these sets, the IN is from AN to BN, you take your A sub n's, okay, you look at the supremum. So first you show that it's bounded from above, that the set of ANs is bounded from above, and then you take the supremum, and you claim that that's in the intersection. And then, how do you show that it's in the intersection? Well, you take an arbitrary interval, I sub n, and you need to show that x is in the interval. And then that boils down to proving that x is between an and bn for all n. Now you know that since x is an upper bound of the set A, then x is greater than or equal to a sub n. And then to prove that x is less than or equal to b sub n, you have to show that each b sub n is an upper bound of A. And then you use the least upper bound property to conclude that x is less than or equal to b sub n. Those are the steps of the proof. Okay. And I also wanted to give this proof to illustrate how to go about learning real analysis, because I think that's one of the questions that a lot of students taking analysis for the first time have, which is, how do you go about learning this? And what we did is a good example. We took a theorem, okay? We thought about what happens if we remove the conditions. Now, do you need to do that to understand the proof? No. But to understand the theorem, I would say that yes, you do need to know what happens if you remove the conditions, right? If you relax the conditions and just, so in this case, we thought about what would happen if you just didn't have a closed interval. Would the theorem still be true just for any interval? And we saw that the answer was no. And then we understood how the proof works, right? And we should also think about where we use the conditions in the proof. So where did we use the fact that these intervals are closed? If you look at the proof, it's a bit hidden, but where did we use this fact? It's the fact, if you think about running the proof involving open intervals, where we use the fact that the intervals are closed is this part. That if x is between a sub n and b sub n, then x must be an I sub n. That's not true if your interval is not closed. So for instance, if you have an open interval, let's say you have an open interval from 2 to 3, right? Now if you have x equals 2, okay, 2 is between 2 and 3, but 2 is not in the interval. That's the key fact where we used that the interval is closed. That showing that x is between an and bn implies that x is in In. That's only true because we knew that In was closed. Okay. Where we used, so that's where we used that In is closed. So this is what you would do for all the theorems. It's like you don't just read the theorem and read the proof. I mean, think about what happens if you relax some of the conditions. Think about when you read the proof, what was the strategy? Try to summarize the proof and also analyze where you use the conditions in the proof, and then what were the facts that you used in the proof. So in this case, we used the key fact that whenever you have a non-empty bounded from above set of numbers, set of real numbers, that set has a least upper bound. Okay. And some other things you can do to think about this theorem a bit more is to prove that the infimum of the BIs, right? So we did the supremum of the AIs. Try to prove that the infimum of the BIs is also in the intersection. That would be a good way to practice. And then there's also other questions you can ask to think about this theorem. Like, would it be true, would something like this be true if you had R2, where you use rectangles instead of intervals? Right? That's a thing to think about. Okay, that's all I wanted to say in this video.